In this video, we are going to look at how to multiply two polynomials in an efficient way. Okay, so we're going to talk about fast Fourier transform, and then in connection to multiplying two polynomials. So so far, we have learned 5 generic algorithmic or algorithm design techniques. So this including the techniques we learned from COM 4040. So these 5 generic algorithm design techniques are: number 1, sorting, traversing, and searching on data structures. Okay, so we learned stacks, queues, binary trees. So those are data structures. And the second technique is divide and conquer. So we use this technique to design faster sorting algorithms, for instance, merge sort, heap sort, and quick sort. So they are divide and conquer. And then we learned dynamic programming and greedy algorithm or greedy selection and linear programming in this course so far. Of course, you know that dynamic programming is actually divide and conquer. So you divide a problem into subproblems, finding recurrence relation, then use a memorization to solve that recurrence relation, right? So these are the techniques we have learned. So today we're gonna look at another technique. That's also another common technique, which is to use math tricks specific to certain problems. So in particular, we're going to look at fast Fourier transform for computing multiplications of polynomials. Okay, so now let's do some review of polynomials. So a general form of a polynomial over a given domain, for instance, real numbers or finite fields, right? So it can be either over real numbers or over finite field, right? So over finite Gelber fields, that kind of thing. And so what we are having here is that we have one variable and we have coefficients. So these A0, A1 up to AN minus 1 are coefficients over the underlying domain. So that is that we have A0, that's the constant term, plus A1x. Actually, here is a 1 here, plus A2x2, plus AN minus 1x to the AN minus 1's power. So in shorthand, we're using a summation notation, so that's written in this way. So we're going to give a name to it about the degree. So this A of S, in this case, has a degree n minus 1. So if AN minus 1 is not equal to 0, then this polynomial AS has a degree of n minus 1. And then we're going to give a name to it, and we're going to say that it is of a degree bound n. So this degree bound n. So this is an upper bound. So this indicates a upper bound of a polynomial, so which means any polynomial with degree between 0 and n minus 1 is of degree bound n. So unless otherwise stated, all polynomials we will consider here have degree bound n. Okay, so now let's see, given a polynomial, how do we evaluate a polynomial on a given point? So here x0 is a given point. We want to find, or we want to evaluate a of x0. So that a of x0 is equal to a0 plus a1 x0 1 plus a2 x0 squared plus a n minus 1 x0 to the n minus 1's power. So this then is equal to, so let's do a0 here. We take x0 out, then we get a1 plus a2 x0 plus an minus 1 x0 and to the minus 2. So here we get x0 out, so we get a0 plus x0, a1, then plus x0, a2, okay, and then plus. So if we put put a3 here, so we get a3 x0 plus a n minus 1 x n to the n minus 3. Okay. So then you just keep on doing, it is equal to this. All right, the reason we do this is to reduce the number of operations, because if you do this directly, you would, so for each, so this will take n minus 1 operations, because you multiply x0 for n minus 2 times, right? So, and then you have a multiplication with an minus 1, so that's n minus 1 times. So all together, you will have n minus 1 plus n minus 2 plus 1 many operations. So this summation is in the order of n squared. Okay, so we want to, so there are n squared, in the order of n squared many operations if you do direct evaluation. So using this rule, using this form, this is called Horner's rule, then we can reduce the number of operations to the order of n. So this is linear. The reason for this is that you look for each parenthesis here. So it has 1 multiplication and 1 addition. So that's 2. So this is 2 operations. Each of these is 2. And finally, that's this 2. Okay, so one multiplication, one addition. So then you have n minus 1, you have n minus 1 such thing. So 2 times n minus 1 operation. So that is the order of n. So that's a point evaluation. So we can do it in linear time. So now we look at polynomial operations. So we have 2 operations. One is summation, the other one is multiplication. Summation is straightforward. So we just add the corresponding coefficients of a particular for each term. So this is a linear. Okay, so this is a linear. There are linearly many operations for summations because you only need to sum up the corresponding coefficients, and you only have you have n coefficients, and you have only n minus 1 additions. Okay, so that is straightforward. So now let's look at multiplication, which is the topic for this video. So, so now what we are having here is we have 2 polynomials. Let's say they have the same degree bound n. So that means ax is equal to a0 plus a1x plus 2an minus 1x to the n minus 1's power. And bx is the same. It's b0 plus b1x. Let me put 1 here. And then bn minus 1x to the n minus 1's power. And then we want to multiply ax with bx. So that means now we look at the terms. Okay, so for instance, the constant can only be a0 times b0, so that's constant. And then for single term x1, you can get, so this is you can get it from a0 b1, or you can get b0 a1. So for x2, you can get a0 b2 plus a1 b1, and then plus a0 b2. So basically, that is that for each j, the summation, the coefficient for this, right? So this is the coefficient, is the summation of, as you can see here, which is a, let's use k, b, j minus k, right? So 0 is 2, and 1 and 1, so which means that so these 2 index, when you add them up, it should be equal to j. And k here is from 0 to j. Okay, so this is a coefficient, and we're going to call this coefficient Cj. So that's what we have here. Okay, so the outcome, Cx, is the product of Ax and Bx. So then this is Cj is in this form. And this form is called a convolution of two vectors, right? So we can represent AX as a vector, A0, A1, up to A and sub A sub n minus 1. Likewise, B vector B is B0, B1, Pn minus 1. Then the convolution of vector A and vector B is denoted by a vector C. And we're going to use this notation, okay, which then is equal to summation, which is a vector. And this vector, the i's, the j's element of this vector C is in this form. So this is called convolution. Okay, so how many operations do we get by multiplying AX and BX directly in this way? Okay, so as you can see here, we have J. So we have how many multiplication? We have J plus 1 multiplication because it's from 0 to J. So we got J plus 1 many. And you got to add them up. So you got J many additions. So that means 2J plus 1 operations to compute Cj. And J is from 0 to 2 to the 2n minus 2 because the highest degree of this two polynomial is 2n minus 2, which is n minus to the n minus 1 times x to the n minus 1. Its coefficient is just a n minus 1, b n minus 1. Okay, so that is the highest term. So that means for each j, it takes this many times. So what you're gonna so that's compute j, and then you have how many multiplication? Sorry. So you just write it in this form. There's no multiplication in this case. So we just write in this form. So j is from 0 to 2n minus 1. So basically, what you're going to have here is, so j from 1. So how many times you do this, it just, so you add them up, right? So j is 0, then you got 1. When j is 1, you got 5. So, well, the easier way you may think of it is just that this is equal to 2j, and j runs from, well, this is greater than, right? It's at least 2j. So when j runs for this many times. So that means that you got 2 and then 1 plus 2, 2n minus 1. So this is n squared. This is n times n minus 1 or 2. So this is n times n minus 1. So it's at least n squared. But the upper bound is also n squared. So direct operations takes the order of n squared operations. So what we want to know here is that can we do better? Can we do better? Okay, so that means that can we do, for instance, can we do linear operations or close to linear, right? So from now on, for computational convenience, we will treat Cx as a polynomial of degree bound 2n rather than 2n minus 1, because it's just upper bound, right? So we can say it for convenience. Okay. Now let's look at, oops. Yeah, let's look at representations of polynomials. So polynomials have two representations. One is by coefficients, right? So this coefficient representation. You just list all the coefficients of a polynomial, so that is a vector. So it's a0, a1 up to an minus 1. It is a vector. And the other one is by point value representation. So as you know that any polynomial of degree let's say n, degree of n minus 1. N minus 1, so you have this many coefficients to determine, but we can just pick n, points, so that they are different pairwise. Okay, so which means xi is not equal to sj for any I and j. And then evaluate them. So we got ax0, ax1, and then axn minus 1. Okay, so we call this y0, y1, yn minus 1. So then what we are getting is this form. So this n points, distinct points at the x-axis uniquely determine this polynomial a of x. Hence, it is another representation. Okay, so computing from a coefficient representation, computing a point value representation, you will first need to compute this, right? So we know that evaluation takes linear time. You have linearly many points, so it takes straightforwardly in the order of n squared operations to come up with a point value representation. Okay, so now let's look at how we can come up with a coefficient representation from a given point value representation. So this process is called interpolation. And the standard interpolation is by Lagrange's formula. So assuming we are given a point value representation of a polynomial, so we got n point value pairs with pairwise different xk, and then there is a unique polynomial a of x of degree bound n. such that yk is equal to a of xk. So for k from 0 to n minus 1, and actually the form of that ax is equal to this. Okay, so you have xk, and then you have yk. So that is a 1 point. So then k0 from k is from 0 to n minus 1. So that's n points, right? So it's 1 point, and then altogether you have n points. And then here, right? So on the bottom, okay, it's just the product of xk minus xj. For j is not equal to k, so it's not going to be equal to 0. And the one on top is x minus xj. For j is not equal to k. So that means that when x is equal to xj, it becomes 0. Okay, so this, as you can see here, that sorry, it's not become 0, because when, so what we're going to look at here is that when x is equal to xk, so what we're getting here is xk, and the one on top then becomes xk minus xj. J is not equal to k. So that is exactly the same as the bottom. So you cancel each other, then it has yk. Okay, so you have yk on that term. And then for any other term, xj, when x equal to xj, because k is from 0 to n minus 1. But let's see, how do I, okay, we don't really care. So we just for, so this is for k. Okay, so let me erase this. So what we are having is that axk, now we know that this is k from 0 to n minus 1. This is yk, and then pi, the product here is j is not equal to k. So this is xk minus xj, okay, for any j. So similarly here is j is not equal to k, xk minus xj. Okay. So now this is a k from 0 to n minus 1, and xk is fixed. So this is, it looks like this. So that means that maybe, all right, so what we are having is this. So let me write it here so you can see it clearly, or you can see it better. So let's say this is y0, and then this is a, let's say k is equal to 3, right? So it's easy to see. So then what we are having here is x3 minus xj, and And here is j is not equal to k. K is 0. Okay. And this is j is not equal to k. Sk, sk, so we still put k here. Sk minus sj. So j is not equal to 0, so j could be k, sk, if k is not 0, because we assume k is equal to 3. So j could be k, so this becomes 0. So that means this term is the whole term is 0. Likewise, only when k is equal to 3, a of sk is equal to yk, because all the other terms become 0. All right. So now, using point and value representations, and then we can also do multiplication by finding. Now we know the product Cx has a degree bound 2n. So what we want to do is to find 2n different points. So what we're going to do is find x0, x1. Well, we just set n different, 2n different values. And then we compute bx, we compute a, axi, bxi, and then so those are yi, and this is yi prime. So then using point value representation, we just need to multiply these 2 points. So what we are getting is x0, y0 point, y0 prime, and then x1, y1 prime, and so on. So then we can get the point value representation of the product of these 2 polynomials. Again, it takes the order of n square operations, because you have these many points. For each point, you need to evaluate a polynomial. So that's for each point, it requires a linear time, and you have linear points, so that it's square, right? So you have about 2n of evaluation to do, and you have 2n terms. So this is just a square in the order of square to evaluate this. And then you have another one. So that is also the order of 2n squared. And then you have this multiplication. You have a 2n multiplication. So add them up. It's still in the order of n squared. So as we said earlier, what we are interested in here is to come up with a faster algorithms to perform multiplication of 2 polynomials. Okay, so it turns out that what we did before is that we can just pick some points differently, right? So we pick them just as long as they're distinct, then we can have point value representation, and then we can just do the multiplication of the values. So if we carefully chosen these points, okay, so if we can choose these points carefully, then we can improve this multiplication from the order of n squared to the order of n log n. So that is close to linear. So that is what we are going to talk about. Okay, so now this diagram gives a relationship between coefficient representations and point value representations. So these are the points we choose carefully rather than arbitrary points. Okay, we choose these points carefully. And then to do this, to come up with a coefficient representation, then we can do it in n log n time. And from two given polynomial, we evaluate these polynomials on these carefully chosen points can also be done in an order of n log n time. So instead of a direct multiplication that takes the order of n squared time, so we are going to go this direction, which then can save the number of operations to from n squared, from the order of n squared to the order of n log n, because this is n log n here, this is n, this is linear, and this is n log n here. So we add them up, it's still in the order of n log n. So then you may ask, what are these points? It turns out that these points are the roots of this equation, x to the n, which is equal to 1. So in other words, you look at a unit circle, you try to divide this circle evenly into 2n parts. Okay. So so now let's just look at, in general, we'll look at complex root of unity. So we are having a x to the nth power is equal to 1. And we know that it has n roots. And we call this n roots as the omega n0, n1 up to omega n minus 1. In this case, of course, omega n0 is equal to 1. And also omega to the nth power is equal to 1, because that is where we start from. So for instance, when n is equal to 2, solving this, x squared is equal to 1, you get two roots. One is 1, the other one is minus 1. So this 1 is omega 20, and this minus 1 is omega 2. Okay, so basically this just means that all these roots divides a unit circle into n equal parts. So evenly, right? So because for drawing purpose, when n is an even number, it is much easier to draw. So in this particular case, we get n, which is equal to 8. Okay, so that is a unit circle. All right. Okay, so now let's look at some properties of these values. Okay. So the first property is called cancellation lemma. So it's a straightforward. So there's omega dn dk is equal to omega nk. So that means this d is canceled for any n greater than or equal to 0, k greater than or equal to 0, and d is greater than 1. Oh, by the way, and there is a, forgot to mention here that this omega n is actually equal to e to the 2 pi I over n. So then omega n to the k's power is equal to e to the 2 pi ki n. So this I is the imaginary unit, which means that this I square is equal to -1. So that's complex numbers unit. And this e to the ui is equal to cosine u plus I sine u. So this is on the unit circle. So that's something we need. So we're gonna just take them as granted without proving them. Okay. All right. So now let's move. Oops. All right. Okay, so we are here. So why is that true? So we can just write it. So this omega dn dk is equal to omega dn dk. So you can write it as dk. And this omega dn is equal to so maybe now remember what we in the previous slide I wrote it. We have this right, omega n to the k is e to the 2 k over n. So now you put d here. You put d here. So what you're getting is 2 pi dk. So put d here over dn. Okay. All right. So you take dk out. We get e 2 pi I over n. All right. So over dn. And then it takes dk out. Okay, so dk is right here, you take it out. All right, but then this is just equal to, actually it's a d canceled, right? So let me write that again. Okay, so I remove this. We write it here. This has a larger space. So W, D, and D. We have e to the 2 pi dk I over dn. So this d canceled. So we get e 2 pi ki over n. So we know this is just omega and k. Right, so this is pretty straightforward. And then from here, now remember earlier we already showed that omega 2 is minus 1 when n is equal to 2. And hence we have the following corollary that says omega n to the n over 2 its power is equal to minus 1. The reason for this is you can think of omega n to the n over 2 to be omega d now is equal to n over 2 times 2. And this k is equal to 1. Right, so k is equal to 1, this is d. So d is n over 2. So then we know this is equal to omega 2 from this cancellation lemma. N over 2 is cancelled. So that is equal to minus 1. All right, so next we're going to see a halving lemma. Okay, so what it says here is that omega n to the k plus n over 2 square. Okay, so we can simply get rid of this n over 2, so that's still equal. The reason for doing this is we know from here, omega n to the n over 2 is equal to negative 1. Then we multiply omega n to the k's power. So from here, we got omega n over 2 times omega n to the k is equal to minus omega n to the k. So this then becomes omega n over 2 plus k is that. So you take a square at both sides, then this negative becomes positive. So that's what we have here, halving. So under square, we can get rid of this n over 2 things. So, so geometrically, it means under square. If you have, now this is a unit circle. So if W and K is here, then you add n over 2 slots, right? So these two are equal under square. If you take square, if you got this, K plus n over 2, half by half. You take square, then these two are equal. Okay, so this is an interesting result. Okay, so from there, we have this summation lemma. So for these unit roots, complex unit roots, you just plug it in to this, right? So you may want to think of it as it's 1 plus x squared plus x to the n minus 1. Let's call this ax. And then for each k, I'm going to plug this in. So this is a xn, I'm sorry, omega. I'm going to plug that in, omega n to the k. Then this is equal to 0. That's a summation lemma. So that's what this means. Okay, for this particular, now this is a particular polynomial. The reason for that, so you can just sum them up. Now remember, when we have this, so R0 plus R1 plus R to the n minus 1 is equal to R to the n minus 1 over R minus 1 when R is not equal to 1. So in our case, as long as this k is not 0, it's not going to be equal to 1. So that's why for any k not 0 and any n greater than 0, this omega nk is not equal to 1. So hence we have this part. Okay, so and then we switch k and n, then we get wn to the n. So we know wn to the n's power is equal to 1 because that's what is, so what we have to begin with, right? So this is a root. So you put wn in it. We put wn as a root in it. So this is equal to 1. So then this is equal to 0. Okay, so this is a summation lemma. All right, finally, that A. So now this is a polynomial we're going to represent. So this is now we're going to look at discrete fast. I'm sorry, look at a discrete Fourier transform. So what we are going to write down is to evaluate this generic polynomial on these unit roots, and then we get yk. So under these unit roots, and the evaluated value, so this is y0 to yn minus 1 is called the discrete Fourier transform of this coefficient vector a0, an up to an minus 1. So this is a coefficient representation. And so under these particular evaluations, so we select particular points on the x-axis. Okay, so these are the points we selected. So now we look at fast Fourier transform. Okay, so we assume that n is a power of 2. So we can use divide and conquered. Then we can rewrite ax in this form. Excuse me. So we're gonna break this original polynomial into 2. So each of them is halved. Okay, so a0 is on all even terms with even index. Okay, and a1x has all odd index, right? So it's a0, a2, a4 up to an minus 2. Remember, n is power of 2, so this n minus 2 is still even. And n over 2 is divisible by 2, okay? And also n over 2 square, n over 2 cube, and so on. They are all divisible. And a1x is all the odd index terms, right? So a1, a3x, a5x squared. So up to x to the n over 2 minus 1. So again, this is divisible because n is a power of 2. Right? It can be divided by 2, and then by 2, and then by 2, and so on until it becomes 1. Okay, so now, so you see this is a polynomial bound n over 2. This is a polynomial bound of n over 2. And the evaluation of a0 and a1, then it only takes n over 2 to evaluate a point. All right, so now you can see that we are getting somewhere. Remember that each time is divide and conquer. So we can divide the original polynomial or the original problem into 2 subproblems. So this is one subproblem, the other one's, this is another subproblem. So you evaluate them and then you merge them back. So it's a merging is one multiplication and one addition. So we can verify this is true, right? Because you put x squared here, you add them up, that becomes, right? You put square, so it's 4, and then it just becomes so this becomes n minus 2. You put square here, so this square canceled. Okay, so that becomes n minus 2. So likewise, you put square here, and you got square 4, and also n minus 1. Yeah, so it's also n minus 1. And then you, sorry, this is n minus 2, because n squared of n over 2 minus 1 is equal to x, n minus 2, because 2 times n over 2 is n, 2 times 1 is 2. So this is n minus 2, n minus 2. But then for this term, you also have an x in front. Okay, you can see that. So this is x. So you can see that add them up, it's just this. Okay. All right. So that is a very clever trick, right? It's a very clever trick. So the first thing is that they use unit roots. The other one is to break the original polynomial into two subpolynomials. So this with a half-size polynomials. Okay, and then we evaluate each of these using the halving lemma. So we only evaluate on these. Now, each of these is a degree bound n over 2. Degree bound n over 2. So we just need 2 times n over 2. So that's n points. Okay, so these are the points we look at. And then we need a square because we put square in here. So that's the points we're going to evaluate A0 and A1. And then combine these results. Okay. So by the halving lemma, okay, so we have n over 2 distinct values in this, because when under the square, remember, under the square, that n over 2 plus k squared is equal to omega n k squared. So that means this will be equal to something else. This will be equal to something else. So only there are n many. So only n over 2 many points are different. Okay. So these are the points. So these are the equal points. So these part are different. So these are different. That you have n over 2 distinct values. All right, so this is a shorter code. It's pretty straightforward. Okay, so we break the original polynomial into two subpolynomials, evaluate on these points. Okay, so and then we just merge them back. So now let's do a time analysis here. So this is divide and conquer. So then we let the t of n be the number of operations to evaluate, to do the to evaluate a polynomial on n points, right? So this is what we did on n distinct points on these unit roots values. So then we divide them into two subproblems, each of them half size. So you get 2 halves, and then the merging. So the merging is takes, so here's the merging part, right? So the merging takes, because for each point, the merging takes one operation and one addition. So we can see that here. Right, so this is for each point. After you evaluate this on that point, you have to merge them back. So each point takes 2 operations. So you have n over 2 distinct points. So that takes the order of n operations to merge. Okay, so that is, we can put it as big theta of n. So that's what we have. All right, so you can just do a run here. So this is 2 times 2 n over 2 square. Okay, plus theta of n over 2 plus theta of n. So what you are getting is 2 square t of n over 2 to the 2. Okay, and then this 2 goes in. So we get, so this becomes theta of n. So we have 2 theta of n. So you keep doing this, then eventually we get 2 to the k t of n over 2 to the k plus k theta n. And when k is equal to log n, 2 to the k is equal to n, and t of n over 2 to the k is just t of 1. So that is a constant. So this part is just in the order of n, and this part is in the order of log n times n. So that's n log n. So hence this is done. So so this just indicates how this yk is evaluated. So for instance, yk by plugging in is equal to this, okay? And then by the cancellation lemma, it is equal to this wn over 2k is equal to wn to the 2k, right? So remember the cancellation lemma is this, the omega dn to the dk is equal to omega n to the k. So when you look at n over 2k, you can think of this as omega you can think of, so let me, you can think of in the other direction. You can think of omega, oops, omega for here. Omega n 2k is omega 2k 2 times n over 2. So this d is 2. So they can cancel. And this is omega n over 2k. So that's why these two are equal. Okay. And then for these, okay, so we just keep continuing this. So we still use the cancellation lemma to show that this is equal to this. Okay, so it's not that hard for this one. It's similar to the previous slide. Okay, so finally, we're going to do this interpolation. So discrete Fourier transform. So we can write it as, okay, so this is y0. So this is the vector of y. which is equal to this matrix. Okay, and times these coefficients. So the coefficients are given. These Wn from Wn k from 0 to n minus 1 are the x values we chose. So that's why y0 is equal to this. Okay, for instance, when you have Wn0, which is 1, so that gives you y0. That's a0 plus a1 omega n0. This will then be a n minus 1 omega n minus 1. So these are ones. So that's just a0 plus a1 plus up to a n minus 1. So that is this row times this vector. Likewise, y1 will be this times this, because you just plug wn1 in, and this is plug wn squared in, so that's what you get here. Okay, so this is also, well, this is linear algebra. And this good thing about this matrix is it is a Vandermonde matrix. The Vandermonde matrix has a good property, which means it's inverse. First of all, it's invertible, and then inverse has a very simple form. So that's omega n to the negative kj over n for the jk's elements. Okay, so this is a proof. Okay, so this is proof that multiply them, it's actually equals to 1 when j is equal to j prime. So this is a straightforward calculation, and that's another clever point. So people thought about selecting special values for x in this form. So we actually made up a Vandermonde matrix at the end, and the inverse is easy to compute. All right, so finally, so we can get this coefficient in this form. Okay, so so the AJ is just the sum of these times n times 1 over n. So so then we can modify recursive Fourier, fast Fourier transform to replace this coefficient vector A with this point evaluation vector Y, and then replace omega n with omega inverse, because the Vandermonde matrix, so we can compute the inverse of discrete Fourier transform also in n log n time. So which means that you can do from coefficient representation to point value representation in n log n time, and vice versa, by choosing the unit root values as your points on the x-axis. Okay. So then finally we have this convolution theorem. So let's say you have two vectors A and B. You want to convolute A and B. So vector A and vector B. Okay, so how do you compute this? So the computation can be done in this form. You compute the discrete Fourier transform, and then you you do the inverse. So it can be done in n log n time. All right, so this is a, instead of n in the order of n squared, you can do a convolution of two vectors in n log n time. So that, so this algorithm is really a, you see all the cleverness in it, okay? So that is also the beauty of using mathematical tricks to come up with nice algorithms, efficient, nice, and beautiful algorithms. All right, so that is the end of this video.